We're going to move on to our next talk here from Joshi, Pattern Recognition Enabled Drilling and Geotechnical Science Support.
Hi, can you hear me?
Yes, I can hear you just fine.
Perfect, thanks. I'm trying to get my webcam started. It's not working. It's fine. Uh, thank you for inviting me. Good afternoon, everyone. My name is Deep Joshi. I'm a recent PhD graduate from the Korar School of Mines. Over the last 3 years, we have been working on a NASA early stage innovation project to develop pattern recognition algorithms for lunar conditions using real-time drilling data. This presentation discusses application of such algorithms in assisting lunar exploration through crewed Artemis missions. Next slide, please. Drilling and collecting subsurface samples will be an important part of Artemis surface activities. These subsurface samples are essential in understanding lunar geology and a necessary step for prospecting the resources that are available there. The Apollo missions, such as Apollo 15, 16, and 17, used the Apollo lunar surface drill, shown here on the right, to collect the core samples during these missions. But these manually controlled drills caused many issues during operations, even injuring some astronauts, and didn't have much instrumentation on them to collect real-time drilling data. Hence, the automated drilling systems can help subsurface sample acquisition process during the Artemis missions. Next slide, please. The objective of our ESI mission was to develop pattern recognition algorithms that can characterize regolith while drilling on the moon. Even though the algorithms that we designed were mainly for robotic missions into the PSRs, they can help to characterize lunar subsurface in near real time during drilling operations that are conducted in crewed Artemis missions. Next slide, please. Before we go into the algorithms and how their applications for crewed missions, I'll briefly talk about the experimental setup and the experiments conducted to build these algorithms. Uh, First, we designed a rotary auger drill there where the RPM was controlled using a three-phase AC motor, and the ROP or penetration rate was controlled through a precision ball screw. The drilling test, you can see the drilling system on the right. The tests were conducted using three different commercially available masonry bits. Next slide, please. During the test, parameters like time, axial force, RPM, and block height were recorded in real time, and drilling parameters like depth, weight on bit, torque, rate of penetration, mechanical specific energy, and normalized field penetration index were calculated. All of these parameters were important in understanding they were really important in understanding the characteristics of the different layers in the samples and understand subsurface properties. Next slide, please. Next slide. Thank you. In total, 87 drilling tests were conducted. 67 of them were in homogeneous and layered analog rocks. They with varying porosity between the rocks. And there were 20 tests conducted in cryogenic sample with four different forms of water ice. Next slide, please. The first form of water ice considered was aqueous icy, where the water ice coats the lunar grains and cements them in place. This uh, this form can either be in high or low porosity. The second form considered was unfused granular icy, where the water grains are intermixed with the lunar grains without any cementation. This form of water ice regolith mixture acts just as a dry soil in cryogenic conditions. And the fourth and final was the fused granular icy, where which is similar to unfused icy with one major difference, where the some of the water ice gets sublimated and refreezes and fuses the regolith grains in place, providing some minute strength to the particle to the sample. Next slide, please. Thank you. One more. Yeah, that's good. Using the drilling data that was collected for all these tests, which were gave us more than 2 billion data points. We designed and trained and validated a pattern recognition algorithm which consists of two regression and three classification modules. Using the algorithm, we can predict drilling dysfunctions, identify layer boundaries, estimate the uniaxial compressive strength of the sample. For most of these modules, random forest was identified as the most optimum method, but for except for UCS, for which wide and deep neural network was the optimum method. Next slide, please. This plot shows the accuracy of the algorithms. For blind test data, the data that wasn't used for training or validation, the algorithm is able to correctly identify UCS for a wide range of samples, and the error overall, the total root mean square error of the test was less than 2 megapascal, showing that the algorithm is extremely accurate. Next slide, please. Another test done to identify the versatility of the algorithm was by creating complex lunar subsurface samples. Uh, in a simulating complex lunar subsurface samples with varying formation thickness and depth. Using the drilling data that we had already collected, the data for 5 digital twin boreholes shown here in the blue boxes was generated, and this raw data was then used for uh, uh, pass through the pattern recognition algorithm. Next slide, please. As the results show here, the algorithm is correctly able to give a qualitative description of porosity for different layers in all 5 boreholes. As you can see, for comparing borehole 1 and 2, there is the one specific layer with layer missing in specific in borehole 2. This was done to simulate pinching of formations, which can be expected in lunar exploration. Next slide, please. The algorithm is also able to correctly identify form of water-bearing regolith for all 5 boreholes. Here you can see that the algorithm adjusts well for changing formation thickness and missing layers, and adjusts the estimation of the form based on that. Next slide, please. With all of that information available, we could also see the real-time estimation of UCS shown here in pink, and the 10-second running average of uniaxial compressive strength shown in the blue line for all 5 boreholes. You can see that the algorithm again correctly adjusts for changing thicknesses and pinching of formations. This shows another application for such algorithms. Here you can correlate different boreholes and identify stratigraphy of the formation using those. Next slide, please. As I mentioned earlier, even though these algorithms were mainly designed for robotic missions, they're just as applicable to crewed missions. Due to their simplicity and versatility, they can be deployed on edge computing systems to retrain on lunar surface during drilling operations. This can be done during crewed missions where astronauts can collect the drilling data as they are conducting the tests, and retrain the algorithms. The algorithms can also be deployed on the lunar surface operation base to track subsurface characterization of lunar surface in real time. This is done routinely in terrestrial drilling operation, as shown here on the right. This is a real-time operation center which nowadays controls the drilling operation for one drilling engineer controls the operation for numerous wells from a single location. Next slide, please. Using the real-time operations using the operation base on the lunar surface with such algorithms, you can the astronauts can track the stratigraphy of the test location in real time, identify drilling dysfunctions such as excessive vibration, bit wear, or auger choking, and acquire a digital core in real time. This can be vital in expediting the resource prospecting of during the Artemis missions. The chart on the right here shows the application of algorithm for a digital twin borehole for real-time application. Due to the optimized runtime, you can get the UCS of the sample in near real time. As you can, such algorithms can, as the presentations of such algorithms can have a crucial role in simulated testing, training of surface drills, control systems, and computing hardware, and help ensure that the Artemis missions are conducted in safe and optimized manner. Thank you. I can answer any questions you might have.
All right. Thank you so much. Remember, put your questions and comments in the chat. I see we do have a good amount of activity in the chat. So please keep that up. That is fantastic. I really appreciate that from all of you.